Alright, so let us start the class. Fine. So, what we learnt was there was a notion of eigenvalues, eigenvectors, then there was a notion of what are called a spectral radius, a spectrum. Alright, the notation for a spectrum was sigma of A, and characteristic roots, characteristic values, and characteristic equations, and so on. Alright, characteristic polynomials. So, recall all of them. So, now what we will do is that we will try to look at some of the remarks which comes from the definition. So, remarks. So, 1, now we are saying that we have not yet proved it, but anyway. So, we would like to say that determinant of A is 0 if and only if 0 belongs to a spectrum of A. So, recall this was the spectrum of A. Alright. So, we are saying that 0 belongs to a spectrum of A. What do you mean by saying that 0 belongs to a spectrum of A? 0 belongs to a spectrum of A basically means this part implies that there exists a non-zero vector x in Cn such that Ax is equal to lambda x, but here lambda is 0. So, you have 0 times x, which is 0. So, what we are saying is that the system Ax is equal to 0 has a non-trivial solution or an infinite number of solutions. Number of solutions, or whatever you want to say, a non-trivial solution. All right, has a non-trivial solution, whatever you want to say, and therefore we know that the matrix A must be non-invertible. So, it must be singular, and hence determinant of A must be 0. Fine. Now, how do I prove that determinant of A equal to 0 will implies that sigma A 0 will belong to that. So, again determinant of A is 0 implies, so determinant of A equal to 0 implies A is singular. A is singular implies that A is not invertible, and this will imply that the system Ax is equal to 0 has a non-trivial solution. All right. So, you can see that all of them, they come together one after the other just as it is. All right, nothing special to be done. Fine. Remark 2. All right. So, what we know is that if I look at any, so let lambda belong to sigma of A. Sigma of A means a spectrum of A. All right. Then what happens is the first choice for us first is that this vector 0 is properly contained in null space of A minus lambda I. Fine. Because there is at least one. So, there is at least one non-trivial solution, and this will imply that dimension of null space of A minus lambda I will be greater than or equal to 1. All right, this is what it says here. Fine. So, therefore, we are saying that this is true if and only if dimension of null space of A minus lambda I is greater than or equal to 1. Fine. In general, I can have whatever the rank, and accordingly I can proceed. Fine. So, if so, fix lambda belonging to C and consider rank of A minus lambda I, consider rank of this. If the rank of this is R, if the rank of this is R, then what can you say about dimension of null space of this? Fine. So, recall that when I had the system Ax is equal to 0, rank of A was R, then there were n minus r. So, A is n cross n minus r linearly independent solutions. You can use either the rank nullity theorem, all right, or you can look at the solution space in the linear system of equations, or you can look at what I call fundamental theorem of linear algebra. From wherever you want, you can look at it. So, since the rank of this, I am fixing lambda, lambda is fixed. For a fixed lambda, if it is r, then this is what I have. The dimension of this will be n minus r. Is that okay? Linear independence, dependence I have already talked about, I will not talk about it. Third one, fine. So, if lambda is, so if lambda comma x is an eigenpair, lambda comma x is an eigenpair for A, then look at A square, then lambda square comma x is an eigenpair for A square. Alright, so let us try to prove this part, and from there build up the idea. So, if I want to look at A square of x, A square of x is A of Ax, which is same as A of lambda x, which is same as lambda times A of x, which is lambda times lambda of x, which is lambda square x. Alright. So, you can see here that lambda square comma x is an eigenpair. For A square. Fine. So, in general, suppose I have got a polynomial f of x which is say a0 plus a1x plus an x to the power n. Suppose I have this, or let me am x to the power m. Suppose I have this. I compute f of a. What I define f of a as to define f of a as a0 times identity plus a1 of a plus a2 a square plus am a to the power n. So, define f of a as this. So, given a polynomial f of x, I am defining what is called f of a. Fine. I would like you to see that, fine, that f of a is a matrix of size n cross n. So, again it will have eigenvalues and eigenvectors, and I can talk of them. So, I would like you to see that, look at this f of lambda comma x, this is an eigenpair for f of a. Why? Because just compute f a of x will be equal to this part times x, which is a0 of x plus a1 times ax plus am a to the power mx, which will give you a0 of x plus a1 times lambda of x plus am lambda to the power mx. All right. See, we have computed this lambda square, fine. So, just you use this to get this part, that everywhere it gets multiplied, all right. And therefore, I get that this is equal to a0 a1 lambda am lambda to the power m, which is nothing but f of lambda times x. Is that okay? So, x remains the same and you get all of them with you, fine. So, whenever I have lambda comma x, an eigenpair for a, I can look at any polynomial in A, and then corresponding I will get eigenvalues and eigenvectors. So, if I am taking polynomial g of A, I will have g of lambda and x as an eigenpair, fine. I am not talking of reciprocal, I am not talking of A inverse here, that is important. Not talking of a to the power minus 1 or a to the power minus m greater than 0. I am not talking of that part, fine. I can talk of them only when a is invertible, that I have not yet come, but you can look at it yourself and do it, fine. So, let us look at some more examples to go further. So, another examples. So, one example that is very important is what is called an identity matrix. Suppose I am looking at the identity matrix 1 0 0 0 1 0 0 0 1, fine. If I have this, then you can see that any collection of 3 linearly independent vectors form a basis of null space of, so in here, in minus, so I should write it nicely, otherwise you will have a confusion here. So let me write a here, I think, a minus I sub 3, all right, is the basis of this, fine. So what you see here is that 1 1 1 belongs to sigma of a, that is 1 is the only eigenvalue, it is repeated 3 times, repeated 3 times, and we have 3 linearly independent eigenvectors. One collection you can take it as 1 E1, this is one pair, another pair is this, and the third pair is this, the standard basis of R3. Or you can take any 3 and then you can do it, fine. 2, let us look at this matrix A, which is 0 1 0 0, all right, fine. So you can see here that determinant of A minus lambda I will be equal to determinant of minus lambda, I am looking at, so minus lambda 1 0 minus lambda, which is lambda square. So this implies 0 and 0, they belong to sigma of A, fine. Now let us look at the null space, or let us try to compute the eigenvectors of this. So let us look at the null space of A minus 0 I, which is same as null space of A, fine. So if I want to compute this, I would like you to see that, so this is all x belonging to R2, or say C2, whatever you want to say, such that Ax is 0, which is same as xy belonging to R2, such that 0 1 0 0 times xy is 0. Now this gives you y is 0, fine. So you can see that this is just nothing but all vector of the type x comma 0, x belonging to R, all right, fine. So this space, this has dimension 1, fine. So even though understand, even though 0 is an eigenvalue of multiplicity 2. Multiplicity 2 means 0 is a root, 0 is a root of characteristic equation, or characteristic root, or characteristic whatever you want to say, of equation, characteristic root of equation. So 0 is a root of characteristic equation with multiplicity 2, with multiplicity 2 means 0 is a root twice. So basically 0 is a root twice, all right. This is what I am saying. We have only one non-zero, or I don't want to say only one non-zero, you will get confused, no, only one linearly independent eigenvector, and we can take it as E1 itself. So you can see that A times E1 is equal to, so 0 1 0 0 times E1, which is 1 0, which is 0 0, which is 0 times E1 itself, all right. So I have got only one eigenvector. So even though I have 0, so even though I have got 0 comma 0 belonging to sigma A, we have only one, so only one eigenpair, only one eigenpair 0 comma E1. See, so recall I had said that whenever I want to look at eigenvectors, fine, they have to be linearly independent. I cannot say that I have this and 0 comma 2 E1, not allowed, all right. So if I am writing such a thing, then this is wrong. I am allowed only one, not more than one. Is that okay? So you have to be careful when you make these statements. So what we are seeing here is that I have an example here where the eigenvalue 0 appears twice, but there is only one eigenvector. So, there is an example where eigenvalue repeats. Fine. So, there was a repetition in the previous example also, which was identity for us, all right. There was a repetition there also, but there we had all the linearly independent eigenvectors. We have 3 linearly independent eigenvectors here, but in this case I do not have 2 linearly independent eigenvectors, all right. There is an example where eigenvalues repeats, but there are not sufficient eigenvectors. Is that okay? So, this is what is important for us. We need to understand this part. Fine. Some more example. All right. Example 3. Fine. You can look at A as 0 0 0 1 0 0 1 0 0 0. Look at this. Or in place of this, just let me put 2 here, 2 here, and 2 here. Then you can see that 2 2 2 belongs to sigma of A. Find out eigenvectors for A, or compute dimension of null space of A minus 2i. Compute this out and check that how many eigenvectors do you get. Is that okay? So, try that out yourself. Fourth, look at this matrix A, which is 0 1 minus 1 0. All right, fine. So, if I look at this, so everything here is real entries. Let us compute determinant of A minus lambda I. So, A minus lambda I, determinant of this will be 0 minus lambda, 1 here, all right, minus 1 here, and minus lambda here. So, this is same as lambda square plus 1. So, if I want to get the roots, eigenvalues of this, so eigenvalues of this will be, you have to write lambda square plus 1 is 0, and this will imply that lambda is equal to plus and minus I. Fine. So, you have complex eigenvalues. What about the eigenvectors? Let us look at the eigenvectors for this. Eigenvector for lambda is equal to I. Fine. So, now looking at lambda equal to I have to solve Ax is equal to Ix, which is same as solving for A minus I times I of x is equal to 0. So, let us solve it for A minus this. So, A is this 0 1 minus 1 0 minus I times 1 0 0 1, which is same as minus I 1 minus 1 minus I. Fine. So, I have to solve this system. So, I will have to do the RREF of this. I would like you to see that this gives me minus I times x plus y is 0, implies y is equal to Ix. You can also write in terms of x using this. You can see here that I can write this as minus x minus Iy is 0, will imply that x is equal to, just look at this, x is equal to minus Iy. Fine. So, whatever way you want, you can do that. So, if I use this part, what I get here is, and just multiply with minus I will get back the old one, alright. So, you are looking at x, which is xy. So, this is same as I want to write all at minus Iy and y the other way, which is same as y times minus I comma 1, alright. So, this implies I and minus I comma 1, this is an eigenpair. Let me check whether I have done it correctly or not, because I am good at mistakes. So, with I it is, I wrote the other way around, I think. Alright, so we are looking at this, and let us see that this is equal to, I can write this also as, so as I said, if lambda x is an eigenpair, then lambda comma Cx is also an eigenpair for C not equal to 0. So, I can also multiply this by I. If I multiply this by I, so I times minus I comma 1 will be equal to minus I square comma I, and minus I square is 1, so it is 1 comma I. So, I comma 1i is also an eigenpair, alright. And this is the one which corresponds to this part, y equal to Ix. This corresponds to y is equal to Ix. Fine. Another example, let A be an upper triangular matrix with diagonal entries d1, d2, dn. Then what we know is that then determinant of A minus lambda I will be equal to, so I am looking at d1 minus lambda, then there will be some things here, similarly 0, d2 minus lambda and something here, similarly finally it will be dn minus lambda, and therefore since it is an upper triangular matrix, determinant of this is nothing but product I is equal to 1 to n di minus lambda, and this will imply that eigenvalues of A are d1, d2, dn. At this stage I cannot talk about the eigenvectors corresponding to di's. Why I cannot talk? Because I don't know how many of them are repeated, how many of them are not repeated, and how they behave. You do not have any information, so you cannot make any statements. All right. So to make you slightly better understand this, let us look at this example A as 2, 1, 0, 0, 2, 0, 0, 0, 2. Let me write this matrix. Let me make it 1 here. I have a 0 here, 0 here, 2 here, 1 here, 0, 2. So look at this 5 cross 5 matrix. All its eigenvalues, the diagonal is an upper triangular matrix, upper triangular with all its eigenvalues too. Eigenvalues to find eigenvectors. So we'll try that out, find eigenvectors. So try that out so that you have a better clarity of what I am trying to say, what are the issues that come into play. Fine, that's very important for us. All right, I have already given you one more example I think I should give, that I can go from real to complex. No, real to complex I have already done, from rationals to irrationals maybe. All right, so let us write A as 1, 2, 1, 3. Let us look at this matrix A. Let us compute the eigenvalues of this matrix. So I need to compute, so till now I have been computing A minus lambda I. Let me compute lambda I minus A. So it's just a polynomial, so I could compute in whatever way I like. So this is same as determinant of lambda minus 1 minus 2 minus 1 lambda minus 3, which is same as lambda square minus 4 lambda plus 3 minus 2, which is lambda square minus 4 lambda plus 1. I hope I have done correctly. I am very bad at calculation, as I said. So this will imply that the roots of this are 4 plus minus b square 4ac upon 2, which is same as 4 plus minus 2 root 3 upon 2, which is same as 2 plus minus root 3. So you have eigenvalues here. You can look at eigenvectors also, you can compute them accordingly. So compute eigenvectors for yourself. All right, so compute them yourself. Then there is also a notion of what are called, so here if I look at what we have done, we have looked at Ax is equal to lambda x, fine. Since I am working over complex numbers, we need to talk of A square of x is equal to lambda of x also. So you recall this corresponds to what you are looking at the column space of A in some sense. Then there is a notion of, or you can say that I am looking at, if you do not want to have this, then I am looking at null space of A minus lambda I, isn't it? So this is equivalent to looking at A minus lambda I of x is equal to 0. So I am looking at the null space of this. So I need to look at what are called left null space also. So I need to look at this also, fine. But the theory will be same, other than here I am talking of A, there I am talking of A star, and therefore I am not going into it. All right. There are some results that if there is an eigenvalue here, there is an eigenvalue here, will they be same, will they not be same, and things like that. can I say that if lambda is an eigenvalue, lambda is an eigenvalue of A, can I say that this will imply and get implied by that lambda bar is an eigenvalue of this, and so on. So, there are theories that you would need to look at it, look at examples and do it yourself. All right. When I come to what are called normal matrices, we will prove some results there, but at this stage I want you to do them yourself. All right. So, we have looked at some examples here. One thing we need to talk of what are called, so we have computed or understood computed eigenvalues and eigenvectors for matrices. All right, n cross n matrices have computed. What do I mean by saying that a linear transformation has an eigenvector? So, question, what do we mean by a linear transformation T from Rn to Rn has an eigenvector? All right. So, recall that since T is from Rn to Rn, fine, I can take an ordered basis of Rn and this will give me, so if I have got an ordered basis here, so this will be an n cross n matrix. So, once I have an n cross n matrix, it is nothing but A of n cross n for some A, and therefore, I can talk of eigenvalues and eigenvectors. Fine. So, I can still talk of in that sense T of x. So, T is some linear map. So, we need to find lambda comma x eigenpair such that Tx is equal to lambda x. So, what we are saying here is that with respect to this matrix, I have got T of Bb with me. I want to find an x such that this is equal to lambda times x. Is that okay? So, you can do it with a standard basis also, whatever way you want, but T of x is defined. So, you are defining T of defined by some rule, and then you are asking for x, all those x for which T of x is equal to lambda x. All right. So, you can look at here, say for example, if I take A as 2 1 1 2, then I can define my T of xy as A of xy. So, this will be equal to 2x plus y and x plus 2y. So, I define T of x like this. Then I would like you to check that if for this example T of 1 1 is equal to 3 times 1 1 and T of 1 minus 1 is 1 minus 1. All right. So, I will have such eigenpairs and eigenvectors here also. So, the idea is that when I want to go to linear transformations from Rn to Rn and I want a eigenvalues and eigenvectors of this, then I am supposed to look at T of Bb for some ordered basis B, get a matrix out of it and then proceed. Is that okay? So, that is all for now. We will look at things in the next class.